Here we present a method for trajectory planning using safe ellipsoidal corridors as projections of orthogonal truss regions. Current powerful approaches to collision-free trajectory optimization divide the collision-free space into safe convex subsets and restrict segments of solution to be within these safe corridors, formulating trajectory optimization as a convex optimization problem. These often require the explicit assignment of relevant time windows to trajectory segments, which can get more challenging in complicated scenarios. The complexity of the resulting convex program is still dependent on the number of convex regions required to represent the solution. We propose a more unified approach to corridor-based optimization. We instead restrict our solution to be within a safe, smooth, and continuous ellipsoidal corridor. We formulate a time-varying affine map that allows us to view the corridor as a time-varying projection of a higher dimensional ball. When projected, every point in the lifted ball traces a collision-free trajectory within the original ellipsoidal corridor. The ball represents a set of feasible parameter values which can be optimized within to find a feasible trajectory. With the quadratic cost, this optimization takes the form of the well-explored truss region problem, which can be solved by a simple search in a scalar variable. In order to increase the qualitative diversity of solutions represented, we instead attempt to find a trajectory in the lifted space. We restrict the set of control points in the lifted space to be within our ball, resulting in a trajectory that stays within our safe corridor. The feasible set of parameters is now the Cartesian product of balls. In order to perform optimization in this set, we develop an orthogonal truss region solver, which divides the original problem into n interconnected truss region problems, leveraging the unique structure of optimization with quadratic constraints. Utilizing this parameterization in tandem with the new OrthTRP solver, we're able to solve for optimal trajectories quickly in spaces that may require multiple convex subsets to describe. In this example, we show a quadrator following a minimum acceleration trajectory in green, homotopically equivalent to an initial guess in red. We compare our method to methods using quadratic programming through polytopic corridors, measuring solve time and solution quality as complexity increases. We utilize the number of waypoints required to represent a trajectory homotopic to the solution as a proxy for complexity. With our continuous corridors and OrthTRP solver, solve times remain nearly constant over varying geometric complexity. This is in contrast to the quadratic programming approach, which scales solve time poorly. Our approach also finds more optimal trajectories in complex environments, while the quadratic programming approach can perform worse than even a naive baseline approach, visualized in red. This is in part because the explicit time allocation restricts the amount of feasible trajectories that can be represented. In this work, we presented a new parameterization of trajectories that represent a more natural approach to trajectory optimization with corridors. We also introduced an approach to solve optimization problems within the Cartesian products of balls. Taken in tandem, these outperformed state-of-the-art approaches in more complicated environments. Future work may see this approach extended to receding horizon context in the configuration space of more complicated systems, or fused for contact implicit optimization with truss regions. Thank you.